Hello! Welcome to today's lesson. It's part of the Kinetics, Equilibrium, and Thermodynamics unit, and we're continuing with thermodynamics. Thermodynamics is a study of energy changes in a chemical reaction. Last lesson, we reminded ourselves that we'd already done this with potential energy diagrams. We were calculating the change in heat, the heat of reaction, or the enthalpy, by comparing the energy of the products to the energy of the reactants. Last lesson, we learned that we could also calculate the enthalpy using heat of formation data. Also, we learned that we can use bond energies, comparing the amount of energy that goes in to break the bonds of the reactants to that of the energy that's released when the products are formed. You had a chance to practice these in our homework assignment, and today's lesson is going to learn about the last way to calculate enthalpy, and that's referred to as Hess's law. Hess's law states, the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes for the individual steps in the process. As you hear this definition, perhaps you're cluing in or keying in these individual steps, and it's triggering a memory, the memory of the reaction mechanisms that we talked about earlier this unit when we were studying the collision theory, or kinetics. So we're trying to come full circle here and put the reaction mechanisms together with the overall reaction, and that same idea holds true for calculating the heat of the reaction. If we know the enthalpy changes for each of the individual steps in the process, then we can add those together and find out what the overall reaction's enthalpy is. So let's just jump right into a practice problem where we're calculating the enthalpy for the reaction. 2 moles of dihydrogen monosulfide gas react with 3 moles of oxygen gas to produce 2 moles of liquid water and 2 moles of sulfur dioxide gas. I'm given 3 chemical reactions that are the reaction mechanism, along with their corresponding heats of reaction. I know this is a Hess's law because I see the reaction mechanism and the corresponding heats of reaction. It's not as simple as just adding these 3 heats of reaction up, however. We need to double check that the reaction mechanisms as they're written are going to match that of the overall reaction. And we do that systematically by looking one at a time. The first species in our overall reaction is dihydrogen monosulfide. I'm now going to try to find it in the 3 mechanisms, and I find it here in the first one. In the reaction mechanism, step 1, it shows up as a reactant. In the overall, it shows up as a reactant. Great. In the overall reaction, I need 2 moles of dihydrogen monosulfide gas. In the reaction mechanism, they're only calling for 1 mole. So here's where we need to start to manipulate the reaction mechanism. I am going to need to multiply the mechanism by 2 so that the number of moles in my mechanism match the number of moles in the overall. If I'm now going to require twice as many moles in my reaction, how will my enthalpy of the reaction be manipulated? You're right, I'm going to have to double that as well. Let's rewrite what we have as a result of this manipulation. We're now going to have 2 moles of dihydrogen monosulfide gas producing 2 moles of hydrogen gas and 2 moles of solid sulfur. And this process is now going to require 10.6 kilocalories of heat energy in order to proceed. How did I get that? It was the 5.3 kilocalories times 2. That's where that came from. Let's look at the next species in our overall reaction. The next species is oxygen. We're going to find where it is in our reaction mechanisms. Ooh, I find it in step 2 and the 3rd step reaction. The fortunate news is that oxygen does show up as a reactant in both of the mechanism steps, and it's a reactant in the overall. The overall reaction requires 3 moles of oxygen gas. Each of the oxygens in the steps of the mechanism require 1 mole, however. It's unclear to me at this point in time which one, or perhaps both of them, I'm going to have to manipulate in a similar fashion to how we did the first one. So I'm going to leave oxygen until the end in the hopes that by looking at the remaining species in our overall reaction, everything will work itself out. So let's move on to the next species in our reaction, the water. Again, let's find where H2O is in our reaction mechanism, and I find it here in the second step. Water is a product in the mechanism. It's a product in the overall. The overall reaction requires 2 moles of water, and the reaction mechanism also produces 2 moles of water. So I'm not going to need to manipulate this reaction in any way. Let's copy it down. We have 2 moles of hydrogen gas reacting with 1 mole of oxygen gas to produce 2 moles of liquid water. And the amount of heat energy is going to be negative 135 kilocalories of heat energy released. Looking now at our final species in the overall reaction, sulfur dioxide gas, finding it in our reaction mechanism, not in the first reaction, not in the second reaction, yes, in the third reaction. Sulfur dioxide gas in the third reaction shows up as a product. Sulfur dioxide gas in the overall as a product. The overall produces 2 moles of sulfur dioxide gas. The mechanism produces 1 mole of sulfur dioxide gas. So this reaction is going to need to be manipulated. Just like we did with the first, we're going to have to multiply this last reaction step by 2, and if I'm doubling the amount of moles, I'm also going to double the amount of heat energy. Let's recopy this. 2 moles of solid sulfur react with 2 moles of oxygen gas to produce 2 moles of sulfur dioxide gas. And this reaction is now going to release twice as much heat, right? That's negative 70.9 times 2. That's what we're doing in terms of our math. Negative 70.9 times 2. It's going to release negative 141.8 kilocalories of heat energy. Now, before we start any more math, we need to double check. Did our manipulations to the reaction mechanisms really wind up giving us what the overall reaction is asking for? So let's combine everything that we've written down here. We're going to add these all together, just like we would earlier in this unit when we were studying the kinetics. I have 2 moles of dihydrogen monosulfide gas, 2 moles of hydrogen gas, a mole of oxygen gas, 2 moles of solid sulfur, and 2 moles of oxygen gas. Again, I took all of the reactants in the 3 mechanisms and combined them all in one here. And then I'm going to write down all the products. 2 moles of hydrogen gas reacting with 2 moles of solid sulfur and 2 moles of liquid water. Sorry, not reacts with, I'm on the product side, produces 2 moles of sulfur dioxide gas. And I'm now going to look and see what, if anything, shows up exactly the same way on the reactant and the product side so that I can cancel them out. I've got 2 H2 gas. I've got 2 solid sulfurs. And that's all I see that shows up exactly the same way. So cleaning this up, what's left are these 2 moles of dihydrogen monosulfide gas. Then I've got 1 O2 plus 2 moles of O2. 1 plus 2, that's a total of 3 moles of oxygen gas, producing 2 moles of liquid water and 2 moles of sulfur dioxide gas. As I now look, this combined mechanism reaction does in fact match what the overall reaction is. So now I can go ahead and do the math. The idea is, according to Hess's law, if I know the individual heats for each of these reactions and I add them all together, that's going to give me the heat of my overall reaction. So the heat of this reaction is going to equal 10.6 kilocalories plus negative 135 kilocalories plus negative 141.8 kilocalories. Let's do that math. 10.6 plus negative 135 plus negative 141.8. Negative 266.2 kilocalories of heat are released in this reaction. That is Hess's law. The sum of the enthalpies for the individual steps in the mechanism will sum to be the enthalpy of your overall reaction. Let's try one more practice problem together, please. Calculate the enthalpy for the reaction. 2 moles of solid sodium chloride react with 1 mole of hydrogen sulfate liquid to produce 1 mole of solid sodium sulfate and 2 moles of hydrogen monochloride gas. We are given 4 steps in our mechanism this time, along with their corresponding heats of reaction. Therefore, I know that this is a Hess law problem. And the idea is, if I can get my individual steps in my mechanism to sum up to the overall, adding up their heats will be the heat of the overall reaction. So let's get started. We took this one species at a time. The first species in our overall is NaCl, solid. We look to see which of the 4 mechanisms has NaCl solid in it, and it's our first step. In the mechanism, sodium chloride is a product. In the overall reaction, sodium chloride is a reactant. Therefore, we need to manipulate the step in the mechanism, and we manipulate it by reversing it. Right? We've learned this unit after we studied kinetics that all reactions are reversible. So I'm now going to rewrite this. Notice the 2 moles of sodium chloride are produced in the mechanism. I need 2 moles of sodium chloride in the overall, so the only manipulation is to reverse this. Let's do that. 2 solid sodium chlorides will now decompose into 2 moles of solid sodium and 1 mole of chlorine gas. Well, if the original reaction released 98,230 calories, if I'm now reversing the reaction, instead of the heat being released, the heat's now going to need to be absorbed. So the delta H for this reaction is now going to be a positive 98,230 calories. Let's go back to our overall. The next species is H2SO4. Find where it is. Oh, here we go. It's in our second reaction of the mechanism. In the mechanism, it's a product. In the overall, I need it to be a reactant. The overall requires 1 mole of H2SO4. The mechanism produces 1 mole of H2SO4. So my only manipulation is going to be to reverse this reaction. Let's rewrite it. H2SO4 liquid breaks down or decomposes into 1 mole of hydrogen gas, 1 mole of solid sulfur, and 2 moles of oxygen gas. If the original reaction released 193,910 calories And now I'm reversing it. Instead of the heat being released, now the heat needs to be absorbed. So the enthalpy of my reaction will now be positive 193,910 calories. Let's go back to the overall. We're up to the third species, Na2SO4. Find where it is in the mechanisms. It's in the third. Na2SO4 is a product in the mechanism. Na2SO4 is a product in the overall. 1 mole of sodium sulfate is produced in the overall. 1 mole of sodium sulfate is produced in the mechanism. Therefore, no manipulation to this reaction is required. Let's simply copy it down. 2 moles of solid sodium plus 1 mole of solid sulfur react with 2 moles of oxygen gas to produce 1 mole of sodium sulfate solid. If we did not manipulate the reaction, that means we will not manipulate the enthalpy. 330,500 calories worth of heat energy are released in that reaction. Looking back at our overall, we're up to our final species, hydrogen monochloride gas. Find where it is in our mechanism. Oh, here it is in the fourth. It is a product in the mechanism. HCl is a product in the overall. 2 moles are produced in the overall. 2 moles are produced in the mechanism. Therefore, no manipulation of this reaction needs to occur. Let's copy it down. 1 mole of hydrogen gas reacts with 1 mole of chlorine gas to produce 2 moles of hydrogen monochloride gas. If we did not manipulate the reaction, we will not manipulate the enthalpy. 22,060 calories of energy are released in that reaction. Hess's law says that if our reaction mechanisms now sum up to be the overall reaction, then the heats of those steps will sum up to be the heat of the overall. So we now check our work. Let's add these all up together. Now some of you can just make these canceling outs as you go. So the sodium chloride decomposed into the sodium and the chlorine elements. I can see that the 2Na is then used up. The Cl2 is used up in a subsequent step. The hydrogen gas that's produced in the second reaction gets used up in the fourth. The solid sulfur that's produced in the second reaction gets used up in the third. And the 2 oxygen molecules that are produced in the second step get used up in the third. So I've canceled everything that can possibly be canceled, and what I'm now left with should match my overall reaction. 2 moles of solid sodium chloride react with 1 mole of liquid hydrogen sulfate to produce 1 mole of sodium sulfate solid and 2 moles of hydrogen monochloride gas. Double checking our overall to what our mechanism summed up to be, and yes, we are correct. So now we can add up all of the heats of our reaction, and that'll give us the enthalpy of the overall. So that 98,230 calories plus 193,910 calories plus negative 330,500 calories plus negative 22,060 calories. When we add all that up, it will give us the heat of our overall reaction. I'm going to do the math in the calculator. You can go ahead and do it as well. Double checking, 193, negative 3. My math tells me that there are 60,420 calories of heat energy released in that reaction. And I do hope that your math and my math match. If I've made a mistake, please let me know. When we're together in our virtual class this week, we're going to be looking at an online lab and working through some laboratory calculations involving Hess's law in action. It is not required for you to do this on your own, but if you're unable to make the virtual class meeting this week, at least you'll know that there was a lab that we had done, and perhaps you can find some time to check it out. But in the meantime, what's next for you is for you to now practice. Open up the corresponding homework from Google Classroom and try out some more of Hess's law problems. I know you'll do great. Thanks for listening, and I'll see you soon.